Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 3, Lesson 6 on working with functions in table form. So we've worked with functions for the last few lessons. We learned the definition of a function and we've even worked with some functions in table form. But today we're going to work with them almost exclusively in table form and this is very important, we're also going to be using our calculator technology to generate tables based on functions that are given in equation form. Now, the technology that I'm going to be using is the TI-Inspire calculator, the most recent TI-Inspire calculator. If you're using an older TI version like the TI 83 Plus or 84 Plus, what I'm going to do will be similar to what you would do, but obviously the buttons that I push will be slightly different. If you use other calculators, let's say like a Casio or a Hewlett-Packard, it will even get more different than that. But all graphing calculators have the ability to do what I'm going to show you how to do today. I just can't show you how to do it on every single type of graphing calculator out there. So if you've got a graphing calculator handy, make sure to have it because I'm going to be using mine at least on some of the later problems in this lesson. So let's jump right into it and let's work with some tables or some functions in table form. All right, we have mostly worked with functions in the form of equations and graphs, but functions often arise in tables as well. So let's jump right into one. Right? It's got no physical scenario, it's just an f of x kind of thing. Let's take a look at exercise number 1. A table is shown below for a function f of x. Answer the following questions based on the table. Letter A just says evaluate each of the following, f of -1 and f of 4. All right, well, why don't you go ahead and do that? That should be very, very quick from the table, and then we'll go through the answers. All right, well, never forget, in function notation, right, the number that's sitting in here is the x value, right? That's the x value, and for that particular x value, we are looking for the output or the y value. So it's very simple. I go over to an input of -1, and my output is 7. Likewise, for this second one, I go to an input of 4, and my output is 12. Okay, we can also think about these as x values and y values if we're really thinking about it on a coordinate grid, but for right now, we're just reading off a table. Now, letter B. Determine the value of f of 3 minus f of -3. All right, we've done these things a few times in the past. I'd like you to pause the video and see if you can calculate that difference. All right, well, first, let's just figure out these values. F of 3 is equal to 15. F of -3 is equal to -9. So that difference is going to be 15 minus -9. Be a little careful there. That's going to be equal to 15 plus 9, and that's equal to 24. We keep seeing that kind of calculation come up time and time again because really what that does is it's telling you how much the function has changed, either increased or decreased, as the x value goes from -3 to +3. So it's increased by 24 units. Let's keep working with this function in table form. Letter C. If this function's graph were created, what would be its y-intercept? Explain. Ah, cool. All right, so what I'd like you to do is pause the video and see if you can figure out, you shouldn't need to plot this function, and please don't. You should be able to tell just by looking at the table what the function's y-intercept is. Pause the video and do that for a moment. All right, by definition, right, the y-intercept is the y value when x is equal to 0. So I go to x equals 0, I look at my output, and my y-intercept is y equals 12. That's it, right? And it's so easy. I don't need to plug it into a formula. I just go, okay, what's the output when the input is 0? That's equal to 12. D is very similar. Let's take a look at that. What are the zeros of this function as indicated by the table? All right, see if you can remember what it means to be the function's zeros. We did that in the last lesson. Pause the video now and take a shot at it. All right, well, very, very similar to the y-intercept. The zeros of a function are the x values where y is equal to 0, right? Where the output is equal to 0. So I'm going to get rid of that. There's a place where the y is equal to 0. There's a place where the y equals 0. But the actual zeros are the x values. So that's x equals -2 and x equals 6. All right. So it's important, right, when we're given a function, to be able to give these function features like y-intercepts and things like, like the zeros. We have to be able to see those in the table themselves. And in order to do that, we have to know their technical definitions. Like, oh, the y-intercept is the y value when x is 0. Or the zeros are the x values that make y, or the output, 0. Okay, let's keep working with functions in table form. As in the last example, it's important to be able to determine the graphical features of functions just by examining tables. Now let's take a look at exercise number 2. Various input-output pairs for 3 functions are shown in table form below. Which of the 3 functions has the greatest y-intercept? Justify your response. Okay, well, pause the video now, look at the 3 tables. We just talked about the y-intercept of functions. See if you can pick out the function with the greatest y-intercept. All right, well, as we just talked about, the y-intercept is the output of the function when the input, or the x value, is 0. So for f of x, the y-intercept is equal to 4. For g of x, the y-intercept is equal to 14. And for h of x, the y-intercept is 11. So g of x has the greatest y-intercept. Right? And it's actually quite quick. Right? Quite easy, quite quick, because we know, oh, all right, the y-intercept is just the function's value, right, when the input is equal to 0. And in fact, the table makes this problem very simple and very fast. Okay, now, very often, data about real-world scenarios involving functions can be given in table form. Engineering, this occurs all the time, where we've got data, okay, and somehow we display it in a table for a function. Let's take a look at one of these in exercise number 3. Cameron is driving their car home from college. The distance they are from home, d, is given as a function of time they have been driving, t, using the table below. Calculate d of 4 minus d of 2 and give an interpretation about what the result means in the context of this problem. Awesome. Well, we did, kind of a calculation like this in the first exercise. Why don't you go ahead and do that and then see if you can figure out what your answer means in the context of what's going on in this problem. Pause the video now. All right, well, before I do this subtraction, this difference, let me first write down what each value is equal to. Well, I need d of 4, right? So d of 4 is going to be the output when the input is 4. That's 123 miles. So Cameron is 123 miles from home when 4 hours have gone by. Let's see, d of 2 is going to be 235 miles. Right? So Cameron is 235 miles away from home after 2 hours. Okay, so I just want to do 123 minus 235. I think I can do that in my head. But just to make sure, not that I can't do it in my head, but I want to be very clear about something, right? Because I'm doing 123 minus 235, I end up getting a negative answer. Specifically, I end up getting negative 112 miles. Okay, so that's actually the answer to what is this thing equal to. Now, how do I interpret that? Well, we have to understand the context of the problem, right? I can't just look at that and go, negative 112, right? Without knowing the context of the problem, or what the function is telling me, this calculation is meaningless. So what this function is telling me is how far Cameron is from home as they drive home from college, right? So what this is telling me is that from 2 hours to 4 hours, the distance Cameron is from home decreases by 112 miles, right? So from 2 to 4 hours, Cameron's distance from home, there we go, from home decreases by 112 miles. Now, side note, let's say some of you out there watching this video, some of you out there wrote down, Cameron got 112 miles closer to home. Awesome. There would be nothing wrong with that interpretation. I just really like to get the word decreases in there because the change in the distance that they are away from home is a negative number, and that indicates that that distance is decreasing. All right, let's keep going. Here we go. Sometimes we may want to produce a table from an equation. This is where the graphing calculator can be particularly helpful. Let's take a look at exercise number 4. For the function f of x equals negative 2x plus 8, do the following. Letter A. Use your calculator's table option to help fill out the outputs in the table above. Now, let me be very clear. I could definitely, by hand, take x equals negative 2, put it into this function, and get an output. Then I could take negative 1, put it in this function, and get an output, etc. But the graphing calculator, that is ideal for this type of use. So, for the first time, I'm going to actually use my graphing calculator for something that it's useful for. For here I am. I'm in a graph, right? Now, I don't actually want to know what the graph of this function looks like, but it's going to produce it for me whether I want to know it or not. So I'm going to put it in. f1 of x is equal to negative 2x plus 8. I'm going to hit enter. Now that happens to be the graph of a line, but I don't really care about that. I'm going to go into my menu where I can put in a table, all right? I have to put in a split screen table. It's a little bit tough to just get a table all by itself. And what I can see in this table, all right, let me kind of step back so that we can talk about it. I know it's going to be a little bit small on your screen, but I see a column for my inputs, my x values, and then I see a column for my outputs, my y values. So I'm just going to translate them from here over to here. I'm going to have to move my calculator out of the way at some point just to be able to write them down, but that's okay. I think we can deal with that. So let's do it. Let's get all these in here. So when x is negative 2, y is 12. When x is negative 1, y is 10. When x is 0, y is 8. When x is 1, y is 6. This is when I'm going to have to move it a little bit. Maybe actually even go down some to get the rest of the table on there. When x is 2, y is 4. 3 is 2. 4 is 0. And 5 is negative 2. So really, I'm just using the calculator to do all of that sort of arithmetic for me, right? The calculator is taking the input, multiplying it by negative 2 and adding 8, and it's producing all of these outputs, right, for these inputs. It's a wonderful, wonderful thing. Again, your calculator might produce tables in different ways than the TI Inspire, all right? That might be something that you have to spend a little bit of time on or talk to your teacher about, or even look at that great user's manual that comes with your graphing calculator. All right, but now let's answer some questions now that we've got our table laid out. Let's take a look at letter B. What is the y-intercept of the function? Well, now that we've got the table, it should be easy. Pause the video now and write down the y-intercept. Well, the y-intercept is the y value or the output when the x value is equal to 0. So the x value is equal to 0 right here, which means y equals 8 must be the y-intercept. Letter C, list any zeros of the function below. Why don't you pause the video and see if you can list any zeros that are indicated by the table. Zeros and y-intercepts are very, very similar ideas. The zeros are the x values where y is equal to 0. And there's only one place where that happens here. It's right here. So my only zero at least that's in this table is x equals 4. All right? Tables are very, very easy to use because it's simple to see the inputs and to see the outputs, much easier than you can do by just the formula. But the great thing is the technology that we are required to use in this course. We have to use it, on certain problems, can very quickly give you those input-output pairs. All right, let's get a little more work with this. Functions can become way more interesting when their formulas contain terms with higher power. So in our last function just had like x to the first in it. But let's look at one that's a little bit more interesting. Exercise number 5. Given the function f of x equals x to the second minus 10 times x plus 16, do the following. Letter A, use your calculator's table option to help fill out the outputs in the table above. All right, well, since this technology is relatively new, at least to this course, let's do this one again together. Okay, so I'm going to bring this up. Now, one thing I could do is I could just totally clear this thing out, which is I think what I'm going to do. I'm just going to go to my file and I'm going to just do a new document. I'm going to say, no, I don't need to do that. And I'm going to add a graph because that's what I really want. And there's my f of x again, right? It clears it out for me. All right, so what do I want? I want x to the second minus 10 times x plus 16. I got to make sure I've got that formula in there correctly. It looks good. I hit enter. Ooh, that's kind of a cool looking graph. I don't really care so much about the graph. I just want that table. So I hit my menu, 7 for table, and enter for a split screen table. My table starts with x values of 0. So there we have it, right? I've got my table up and I can just start reading those pairs off. When x is 0, y is 16. When x is 1, y is equal to 7. So let's write them in. Here we go. 0, 16, 1, 7. Let me just get that out of there. 2, 0, 3 is negative 5, 4 is negative 8. That's about as far as I can go there. And then I need to shift and move this down. 5 is negative 9, 6 is negative 8. 7 is negative 5, 8 is 0, 9 is 7, and 10 is 16. This is what's known as a quadratic function. We're going to work with those exclusively in a couple more units. They're pretty complicated functions, but the great thing is we don't need to know much about their formulas or anything like that. We can now answer a bunch of questions about this function just based on this table of values. So let me scroll this up a little bit and let's talk about letter B. What are the zeros of the function that appear in the table? So, by the way, before answering this question, let me point out one of the biggest limitations about tables. Tables only show you what you've asked it to show you. In other words, all I can see are the input-output pairs for a domain that goes from x equals 0 to x equals 10. And on top of that, the domain only has integers in it, right? So I don't know what's going on at 1.5 or what's going on at 4.75. I don't know what's going on at x equals negative 22. I don't know any of that. But based on the table alone, what are the zeros that you see? Pause the video down and go ahead and write them. All right, I'm going to keep harping on this. The zeros are the x values where the output or the y value is equal to 0. Here's a y value equal to 0. Here's a y value equal to 0. So my zeros are the x values, x equals 2 and x equals 8. All right, now here's a little bit of a trickier one we haven't talked about yet. C asks us the following. Does the function appear to have a turning point? If so, what are its coordinates? All right, I want you to look at this function and remember, a turning point occurs where a function transitions from increasing to decreasing or decreasing to increasing. So when the y values change direction from going up to going down or going down to going up, then you have a turning point. See if you can find the turning point in this table. All right, well, let's take a look at the outputs and see what's happening. Right, we have an output of 16, which decreases to an output of 7, which decreases to an output of 0, decreases to an output of -5, then decreases to an output of -8, decreases to an output of -9, increases to an output of -8, increases to an output of -5, increases to an output of 0, etc. Where did that change happen? That change happened right here. Now, that doesn't guarantee that's a turning point, but there's some real good evidence in the table that that is likely a turning point because our function was going down, it was decreasing all the way to here, and then it's increasing all the way to here. And also notice that symmetry in the table. -8, -8, -5, -5, etc. We're going to be exploring that a lot more when we look at quadratic functions in depth in a few more units. But for right now, hopefully, you can kind of understand in the table why that would be the location of a turning point. All right, let's keep using the technology. Exercise number 6. The function g of x equals x to the third minus 4x squared minus 31x plus 70 has 3 integer zeros on the interval -10 is less than or equal to x is less than or equal to 10. Set up a table on your calculator to determine the values of the zeros. All right, so we've done this twice now. I'd like you to take a shot at this on your own. It might be a little confusing because of that x to the third, but then we'll go through it and we'll use that technology to find those zeros. Pause the video now and see if you can figure them out. All right, let's do it. So, bringing back out my TI Inspire. I'm going to go and I'm going to, again, start a new document. It's just kind of quickest. I'm going to add a graph. Here we are. All right, now to get the third power, we have to use that caret button that you've surely used in other, graphing calculators and things like that. So I have x to the third minus 4 times x to the second minus 31 times x plus 70. All right, I hate the fact that my cursor is stuck right there, but that's okay. Let me hit enter. Ooh, wow, look at that. That is a crazy looking graph. I don't even know what it looks like because of my window. Now let's get ourselves a table, right? Just like before, I'm going to hit my menu. I'm going to go to option 7, which is table, and I'm going to put in a split screen table. And I'm actually going to go all the way to x equals -10, right? Remember, this problem says that I have 3 integer zeros on this interval, meaning that there are 3 values of x for which the output is equal to 0, somewhere between -10 and 10, and they're all kind of whole numbers with negatives, possibly. So I'm just going to hit my down button, right, until I find, oh, there's an output of 0, right? When the input was -5, the output was 0. So x is equal to -5 is 1, 0. All right, well, we found one of them. Let me just keep panning down. Oh, there's another one, right? So now when x is equal to 2, y is equal to 0. So x equals 2 is another 0. And finally, there's got to be another one in here or the problem's lying. There it is. When x is equal to 7, y is equal to 0. So it's amazing. There's actually an algebraic technique for finding these 3 zeros that you won't even learn until probably pre-calculus, right? You might not take that until like your senior year in high school, maybe even your freshman year in college. But we can find these things without algebra by simply putting the function into our graphing calculator, generating a table of values, and then just looking through it. Isn't that kind of cool? All right. Let me move my TI Inspire out of the way. I think that's maybe the last time we'll need it, but I'm not sure. Now we'll need it one more time. Exercise number 7. A rocket is launched into the air such that its height as a function of time is given by the equation h of t equals negative 16t squared plus 144t. Use a table on your calculator to determine when the rocket reaches its maximum height. All right, so a few things, right? One, this is one of the first times we've seen function notation where the input variable isn't called x. Whatever, it's called t, and that makes sense because it's t for time. But when I use my graphing calculator for this, what I still really want to put in is f of x equals negative 16x squared plus 144x. All I'm doing is changing what the input and output variables look like. So here's what I'd like you to do. I'd like you to put this into your calculator, and I'd like you to play around with your table. And as a little hint, my bet is on the first shot using your table, you might not quite get this answer right. So take a look, and then we'll revisit it. All right, I want to figure out the time when the rocket reaches its maximum height. So let me bring out my TI Inspire. Doc, file, new document, no, add a graph. Great, here we go. Negative 16x to the second plus 144x. Now there's something that's tricky about this. All right, menu, table. Enter. All right, I'm going to go up. So I'm going to write out this table here so we can see it nice and big. Okay. I've got x, I've got h of x, whatever, f of x, it doesn't matter. All right, at 0, I'm at 0. That kind of makes sense. At 1, I'm at 128. At 2, I'm at 224. At 3, I'm at 288. Notice like the rocket continues to go up, right? Its height, which is the output, keeps going up. At 4, I'm at 320, and then I can't see any more of my table. So at 5, I'm also at 320. At 6, I'm at 224. And I think I'll pause there for a moment. Right, so I've generated this table, and let's try to interpret what's going on, right? Remember, this is my time, x is my time, and h is the height of my rocket. So first we're at a height of 0, makes sense, we're shooting the rocket off from the ground. After 1 second, it's 128 feet in the air. After 2 seconds, it's 224 feet above the ground. At 3 seconds, it's 288. At 4 seconds, it's 320. Notice it keeps going up, right? And at 5 seconds, it's also at 320. And then at 6 seconds, it's at 224. And if I looked at 7 seconds, I would find out that it was at 128 again. Now, let's just think about this for a moment. All right, I mean, if you just threw something up into the air and then it came back down, okay? At some point in time, one moment in time, it's gonna hit that top height and then it's gonna start to drop. Makes sense, right? There's probably no chance it's gonna go up and hover for a second. So somewhere between 4 and 5 seconds, I'm hitting my maximum height. Sometime between 4 and 5 seconds, I'm hitting my maximum height, but it's not at 4 seconds or 5 seconds. That's actually the wrong way to look at it. What I'm gonna do now is I'm gonna go into my table and play around with it a little bit, right? I'm gonna do that by hitting menu, and I get this little option that allows me to play around with my table. And one thing it does is it allows me to edit my table settings. So I'm gonna go down to option 5, edit table settings. And it basically says, hey, where do you want your table to start? That's my x value. Well, I'm pretty sure I hit my maximum height between 4 and 5, and then it says table step. Now, this is something I want to talk about. Table step, which I realize you can't really even read from there. But your table step is how much your x value increases each time. So right now, the default is 1 unit. In other words, it goes from 4 to 5 to 6, etc. I'm going to make it go by tenths. I'm going to have it go by tenths of a second. All right? So let me go 0.1. Okay, enter. And now look at my table. Right now my table has 4, 320, 4.1, 321.44, 4.2, 322.56. So we can see that those heights are continuing to go up until I hit 4.5 seconds. And at 4.5 seconds, right there, I can't draw on it, right there at 4.5 seconds, right, we hit our peak height. Right there at 4.5 seconds, we hit a peak height of 324 feet. So, right, it says use a table on your calculator to determine when the rocket reaches its maximum height. It doesn't even ask what the maximum height is, but it reaches its maximum height at 4.5 seconds. Right. And that's a little bit of advanced work with tables, right? Because normally a table will only have integer values in it for x, okay, and then the outputs will be what they are. But you can refine a table. You can actually go by smaller steps by going into your table settings. And we'll work with that more as the year goes on. For right now, though, I'm just going to move my TI out of the way, and let's wrap this up. Tables are wonderful ways to both represent functions and to understand various things like y-intercepts and zeros and behaviors. All right. So in this lesson, we really kind of worked on two things. One thing was just, here's a function given to you in a table form. Answer a bunch of questions. What's the y-intercept? What's the x-intercepts? What are the zeros? You know, things like that. But the other thing that we did is we used our technology for the first time, really, to take advantage of the graphing calculator's abilities to put in a function's formula and generate a table's value based on that formula, right? And again, we looked at some pretty sophisticated techniques, especially in that last problem. So get some work on this. Make sure to understand how to use the technology that you're going to have for this entire course. We want to be able to use it to the best of our ability, all right? And again, that might mean talking to your teacher if you're not using the calculator I am, you know, or opening up an instruction manual. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.